Hey everyone. So we're going to get started. So hi, my name is Nick. Today I'll be presenting the Introduction to Machine Learning with Scikit-learn workshop. So this is a lot more of a talk than a workshop. There's not much of an interactive component, but all the code is available in a notebook later on, which I encourage you to play with because we won't be focusing too much on that today. So before I start, I'm going to plug Data Science Club. So I'm a part of the University of Waterloo's Data Science Club. We are a club who hosts workshops, different events related to data science, like resume critique, co-op panels, we have reading groups. It's a great time. Check out our Facebook page and group. I will link the slideshow to you so you can just click those links. And yeah, stop by our office anytime. There's always someone in there. We love to chat. It's a great place to learn about data science and get more involved. Cool. So just a quick overview of what we're going to be covering today. We're going to be covering some basic concepts and terms in machine learning. Then we're going to get started with decision trees and random forests. So these are two machine learning models that you may have heard of. Super robust, super cool. You'll enjoy that. And then afterwards, for the second half of the workshop, we'll focus on understanding your models and interpreting your models and seeing how we can improve your models. So here are a few resources. The first bit.ly link is the one you really want. It will take you to the slideshow, and you can click all the links on the rest of the slides. I encourage you to type this in right now. The next thing is a GitHub repo with a notebook. And so I have a whole notebook, going through all the code that I present today on these slides today, plus some more. I'd highly encourage you to look at that. At the very top of that notebook, there's an Open in Colab link. Click that link, and you can run all your code in the browser, so you need no dependencies on your end. And yeah, it's a great way to get familiar with that stuff. Second link is actually a link in Colab. The Fast AI ML course. So I guess I say this early on, just in case you're not paying attention. So this is the course I highly recommend. It's a 6-video course, so I don't know how many hours that is, but it covers a lot of the stuff I cover in this workshop, plus more. So if you enjoy the content here, highly recommend checking out that course. It's excellent, it's online. I cannot recommend it enough. Finally, there's my contact information there. I got to plug my Twitter. I made it this summer, and I tweet ML stuff, so you should follow it. And yeah, feel free to reach out to me about anything in this workshop, anything in my previous workshop, or anything you Waterloo stuff like co-op or courses about data science, etc. I'm super happy to help. Great. So let's get started. What is machine learning? So today we're going to talk about a specific kind of machine learning called supervised learning. And basically, this is where you take some input X, which I'll commonly refer to as features throughout this workshop, and we're going to predict Y. And so we're going to call that the target. And the idea is you have a lot of data where you have both X and Y, and you're going to train something called a machine learning model to understand the relationship between X and Y. So a very simple example is linear regression, Y equals mx plus b. So suppose you have some weather data. You have the day of the year, and you want to predict weather. So day of your year is your X, and Y is the temperature outside. And so this is a super simple machine learning example. You want to find the best M and B that fits the best line to your data to predict the temperature based on the day of the year. So that's a super simple example. And of course, this scales all the way up to super complex models machine learning models that will identify cats or dogs in images, or translation systems that take in input from one language and translate it to another. Our focus today won't be on the latter. It'll be more on the former, where you have some tabular data and you're trying to predict something from that. Any questions from this? Great. So what is regression? So this is what we're going to be talking about today. And essentially, it is a type of supervised learning, which I covered in the previous slide. There are two types of supervised learning, regression and classification. Regression is where, given some input, you're predicting a number. So the example I gave you before, predicting the temperature given the day of the year, that would be a regression task because the temperature can take on any number of values. Classification, on the other hand, is when you want to identify if the input is in some category. So this is along the lines of, oh, given an image, is this a cat or a dog? And so that's a classification task. And so we're going to be focusing on the former today, regression. And so the first thing we're going to cover is understanding how we can evaluate our model. So the very first step is to know if our model, like no matter what our model is, if it's good or bad. And so there are two ways we're going to do that today. The first way is something called mean squared error. Don't worry about the math on the screen, but it's there just in case you want to look at it. But essentially, we're measuring the discrepancy between like our model's prediction and our actual result. So here you can see that, don't worry about what the symbols mean, but we're basically taking the difference between what our model predicts and the actual answer and squaring that distance and just basically summing it over the examples that we have. You'll see what this means a little bit more when we actually start using it. The second thing is called coefficient of determination. Again, ignore that equation, it's there in case you want it. But essentially, this is a value from like negative infinity to 1 that describes how well your data is describing your target variable. So how good your x is for describing your y. And so if the value is close to 1, that means your model is doing a great job. And if your value is close to 0 or below 0, your model is doing a very poor job. For a more intuitive explanation of this metric, basically you can think about it in this way. So the thing you're trying to predict has some variation, and your data also has some variation. And so this R squared metric essentially does 1 minus the ratio between like what variation there is in your y. So like I guess the numerator there is like your mean squared error essentially. What variation is accounted for by data divided by what variation there is like inherently. If you didn't get that, don't worry. But essentially just know that a value closer to 1 means your model is doing a good job, and as you get lower, it's worse. So I said a lot of words there. Any questions? Yeah. Please feel free to ask questions, like clarify terminology, or like ask. Like I love questions like, "What's the point of this?" Because like that'll really. I believe that like if you understand why you're doing something, it's like much easier to figure out how to do it. And so yeah, please feel free to ask questions. And also, just to clarify, I've been saying the word model a lot. For the purpose of this workshop, just think of model as some machine, okay, that's a poor word, some function that takes in your input and gives you back your y. Questions? Yep.
So these techniques are usually used only for linear regression models, or?
Good question. No, these two are pretty common for any kind of regression, like a regression model, but linear regression is one example of those. Yeah. Any other questions? Great. Cool. We're going to talk about two concepts here, which are very important, and you'll see why they're important as we go throughout this workshop. And it's the idea of underfitting and overfitting. And so I think these pictures explain this like perfectly. So basically, given like your input, let's say for example it's time, you're trying to predict this value, and this line is what you're using to predict that value. So as you can see in this first example, this is an example of underfitting. This line is not doing a great job at capturing the trend in our data. Like clearly this a linear, like it's not a linear trend, right? It's like a curved trend. And so that's what we call underfit. Essentially our models was not able to capture the pattern that our data follows. The second plot here is like a good or a robust fit. And so like that looks like a good fit for the data, right? It just describes the general trend, and you could rely on predictions from that model. The last one is something called overfitting. And so this is essentially when your machine learning model like memorizes your data. As you can see, that line passes through every data point. But to the human eye, it's clear that like that's not the trend of the data. That's just some noise that the model is learning. And so ultimately, this will result in the model like doing very poorly in when you actually use it for your task. And so it'll look really good on your training data, like it got perfect, it got all the data points. But when you actually move on to use it in the real world, it's going to do very poorly. Any questions about these three? Yeah.
Is it the relation between the expected value to the predicted one? Is the graph between that, or?
That is slightly different but related. And so if you look at, if you fit a model purely on the expected value based on the data, often you'll get an overfitted model. So really, you don't want to always do that on like an unconstrained model. We can talk more afterward, but if you fit like the expected value on an unconstrained model, you'll often get overfitting. But if you have like a constrained model, like just a line, then fitting the expected value is exactly what you want. but sometimes the line is not flexible enough to fit your data, like this example. We'll definitely chat more after the workshop. Any other questions? Yep.
Sorry, can you explain again why
Sure. So let's actually draw this on the board. If you imagine that here you have your time and values, and let's say you have some like the data that your model's trying to learn, right? So you have something like this, and so your model might fit like this is super overfit, right? And so now let's say you want to make a prediction like in the real world, like you're deploying your model, like oh you trained your model on this data, now you want to actually use it to forecast the weather for the future, right? And so let's say that well first of all, it would be in the future for time. Let's say the data, like the next one is here, which would make sense, right? Because the data looks like it has like a general trend like this, but this model is going to do very poorly. Like the prediction is going to be completely off, because like the line that you fit is just memorizing this data. Or for example, if you're trying to make a prediction here, if you had like a well-fitting line, like this would have done great. But this overfitted line just memorized the data, and so this prediction is the prediction the model would make, which is right here, is going to be not very good. Does that make sense? Cool. Anything else? Great. So the last concept we're going to talk about before moving on to our actual machine learning is training, test, and validation sets. So as I mentioned, we want to prevent those two scenarios that we talked about before, which is underfitting and overfitting. Really, we want a good line to represent our data. And so in order to do this, we use this technique, which I will explain now. And so essentially, you have your data set of labeled examples. And so the running example I'm using for now is like temperature versus your day. And so you have a whole data set of examples of like days and temperatures. And essentially, you split this up randomly into 3 subsets. The largest subset is your training data, which your model is actually going to try to learn. The second subset is called the validation. The last one is test. So your validation set is used to tune hyperparameters. Those words mean nothing to you right now. They will eventually. But just know that your test set is used to evaluate your model. So to be clear, you're training your model on this training data, whatever training means, which I'll explain, and you're evaluating on this test set. And so why do we do this? This will actually help us identify overfitting. Because if you think about it, if you have a super overfit model, you won't be able to tell just based on like the training, like the metrics you use on your training data, because your model learned those. But when you have a test set, and so like training examples that are outside of your data, then you'll have a good idea of how your model would actually perform in the wild. You can think of it as like a precept to actually deploying it. And so that's why we have a test set. Any questions about what I just said? Yeah.
So you said the 5 and 60, 20, 20, and 70, 30, 30.
Yes. My math is not, that's why. We should have said 70, 50, 50, thanks for the question. But yeah, if you want to touch on that, I will. But any other questions about what I said? So yeah, to be clear, your model learns the training data, evaluate on the test data. Essentially, it's like giving your model a test. You're not going to show them all the questions before they write, like so they can study the questions, right? You're going to show them different information, and they're going to write the test with different questions. That analogy, I tried. So this 60-20-20 split is basically a common way to split your data. And so if you have like, let's say 1,000 training points or like 500 training points, these are like very common splits. And so 60% of your data is used for training, 20 for validation, and 20 for testing. As your data set size grows, I would say that your training data grows, but your validation size stays the same. Like in my experience, your validation and test sets don't need to be larger than like 5,000 examples. And so if you have 1 million data points, you can have very tiny validation set like 5,000, test set of 5,000. Essentially, you just need enough data in these two sets to like evaluate your model and understand how well it's doing. And you'll see where that comes in when we start fitting these models. Yep.
How do you decide which data points will be trained and which ones won't?
Good question. Usually it's a random split, but this is not always the case. So for example, if you're working with data that has to do with time, you typically don't want to do a random split because, so let's say you're like working with tax, so the weather example as always. If you do like a random split, you take random data points, your model is still like learning about those data implicitly because like it covers the same time range. It would make more sense that your training data is like the earliest portion, and then your next portion is the validation, and your last portion is the test. So like you're kind of predicting into the future. If you didn't catch that, don't worry, it's not too important for this workshop, but I would check out that course. They talk a lot about properly splitting your data. But for the purposes of this workshop, it's a random split. Any other questions? Great. Cool. Now that we have like some of these foundational concepts down, we are going to actually take a look at some data. Well, we're not going to look at the data, but we're going to use it. So the data I'm going to show you is from the Boston housing data set. Essentially, this has a lot of attributes about houses, like the size, the overall quality, the location, the number of rooms, et cetera, et cetera. And so given this information, we want to predict how much it was sold for. And so I have a link here in the slideshow. You can click the link and check out the Kaggle competitions. I highly encourage you to check out notebooks that other people have created. I think it's a great way to learn how to do machine learning and see how other people do it. And so again, these slides will be available afterward. Follow that link, check all that stuff out. So this data set has about 1,500 examples. So when I say an example, that's like one house that was sold. And so that includes all the information about the house and the sale price. Yeah. In this workshop, we're kind of cheating. We're kind of skipping the hardest part of machine learning, and that is like cleaning your data and pre-processing your data. I would say like if you're doing like data science in the field, or if you're some kind of machine learning engineer in the field, 90% of your time is spent processing the data, cleaning the data, iterating over this data. So when you build a model, you'll assess your model, and you'll say, oh wait, no, there's something wrong with my data, and you go back to the data. And this is like a big part of your job, and this is kind of what my previous workshop covered, if any of you were there. But if not, there will be a link to that one too. So we're skipping all that hard stuff, and we're doing the easy stuff, which is fitting the machine learning models, as you'll see. But just to get like a brief overview of what you should have done before actually fitting a machine learning model, you should definitely explore your data, understand your data. What kind of values does it take? What kind of examples are there? Like you should plot histograms and scatter plots, understand relationships. You should definitely like clean the data, which means put it into a form that's suitable for modeling. So this involves like filling in null values. Your data is not going to be perfect. You have to deal with these somehow. You should be correctly formatting categorical and ordinal variables. So let me explain what those are. Categorical variables like means that it's literally if the example falls into some category. So for example, for a house, if it's like a condo or a bungalow or a two-story house, like, those are 3 categories. And so that's what I'm going to call a categorical variable. An ordinal variable is basically categorical, but it has some order. So for example, like let's say we're talking about the house and we're talking about the ceiling, and for some reason we're using like low, medium, and high. So that's an ordinal variable, or a feature. Sorry, I should be using the word feature. That's an ordinal feature. It has some order, but there are distinct categories. Any questions about anything I said? Great. So if you had the Bitly link in the beginning of the workshop, you'll be able to open up the notebook, and that shows you the data. You'll have a more concrete idea of how that looks. But yeah. So now we're going to look at some actual code. This is just some basic setup. So we're using a library called Scikit-learn. Scikit-learn is a machine learning library available in Python. It has a lot of common models, such as linear regression, logistic regression, some of the models we're going to talk about today, et cetera, et cetera. Super easy to use. It's super convenient. I would highly recommend it for whatever machine learning you're trying to learn or do. And so let me just explain the code that's on the screen right now. The prerequisite in quotations to this workshop was the previous workshop, which talked about pandas. If you don't know how to use pandas, don't worry. This is probably the only slide that uses it. So basically, we're going to split our data set up first into X and Y. And so as you can see, don't worry if you don't know pandas, but basically dfy will contain all the sale prices, and dfx will contain all the other information. So information like the size of the houses, quality, et cetera, et cetera. The next thing we're going to do is split it into a train and test set. So earlier I talked about having, train and a validation set. Earlier I talked about having 3 sets. For this workshop, we're only going to use the first 2, just for simplicity's sake. But in real life, you would also want to have a test set. And during the end, we can talk a little bit more about what you do with these sets. Cool. We're going to define a metric called root mean squared error. So during the first slide, I told you about a metric called mean squared error, and this measures how well your model is doing. Essentially, when the value is lower, your model is doing better. Root mean squared error is exactly that metric, except you take a square root. The reason we're going to use this metric today is because it's just a little bit easier to understand. If you think about mean squared error versus like the price, the unit of measure is like $squared, and that's not very easy to understand. Whereas root mean squared error, oh, is this mouse moving? Sorry, that's annoying. Whereas root mean squared error, the unit is in dollars, and so it's a little bit easier to understand how well our model's doing. We'll definitely see that in the coming slides. This last function, I was debating whether I should even include this or not, but I did to show you some Scikit-learn. So essentially, we're going to use this function to print out how well our model is doing. And so model.predict, essentially what that does is, given your data, so like your x's, it'll like predict out the y's. And essentially, we're measuring the root mean squared error between the prediction and the actual values. Cool. So that's the first line. The second line will give you the r squared. And so if you remember the earlier slides, we talked about mean squared error and r squared. So this first line is the mean squared error for the training and the validation. The second row is the r squared. And I just print that stuff out. So that was a lot of words. Any questions about anything I said? I'm happy to like re-say it. Yep.
When it says test size 0.2, does that mean that it's 20% test and 80%?
Exactly. Yeah. Thanks for pointing that out. I should have said that. Yeah. Exactly. Yes. Any other questions? Yep.
Where do you define the model?
So model is actually something we're going to pass in as an argument to this function. We'll see how we define the model in the next slide. Yeah, this slide is just some setup so you know what functions I'm calling. Yeah, it's totally cool if you don't. Yep. Yes, so df_y is, are you familiar with pandas at all? Don't worry. So it's basically an array containing your y values. And so these are like the sale prices. And then dfx, you can basically think of that as a 2D array containing all the information from your data set. And so this involves like the size of the house, quality of the house, etc. So each row is like one house, and each column represents like one feature. So a feature could be like the quality, the feature could be the size of the house, and so all the information is here. No worries. Anything else? Great. So the first model we're going to look at is something called a decision tree. So this is a pretty simple model. It's a pretty intuitive model. And we'll see that we're going to build on this and create a very powerful model that will actually get you like world-class results on a lot of data. And so to start here, this is a decision tree. And so essentially how this works is you start at the top of the tree, and you, given these conditions, you go down. So I'll explain what that means. So you start at the top of the tree. So let's say you have a piece of data, and so data about a house. So this involves, as I mentioned before, like the size of the house, quality, etc. You start at the top of the tree, and you check that condition. So there's a feature called, I don't know what GR stands for, but living area. So we're checking if living area is less than 749.5. And if this is true, we're going to go to the right branch, and if it's false, we're going to go to the left branch. And so let's say it's true for the house that we have, and we go to the left branch, we check the basement exposure. So this is probably a true-false variable. So less than 0.5 means false, greater than 0.5 means true. So let's say that's true, that's false, and so we go down to this branch here. And essentially, given this information we have, we keep going until we reach the bottom of our decision tree, and now our prediction is this value right here. And so for this imaginary house that I just made up, the value we're going to predict is, okay, it was sold for $8,750. Does that make sense? Does anyone want me to do that again? It's like pretty intuitive, like how to use a decision tree. Great. Yeah, so this is a super simple model. Let's see how we can actually build one given data. Great. Cool. So we are going to build a decision tree using a small subset of data that we have. And let's say, for example, this is all the data we have. So when I say all the data we have, this is all the training data we have. We will also have some like validation and test data we're going to use to evaluate our model later. And so we have the year that it was built, we have this overall quality, and then we know the sale price. And so given these two things, we're trying to predict the sale price. So using the terminology I used before, our features are the year built and the overall quality, and the target is the sale price. So the first step in building a decision tree is to start with a node. And so essentially, that's our node right there. And I'll tell you what all those numbers mean. So the first one is the mean squared error. So basically this is, before that, so basically this node is like a start of a decision tree. If you just use this node to make predictions, the prediction would always be the value over there, which is 183,000. And that 183,000 is the average of all the examples in our training set. And so as you can see, the values are prediction, samples is 4. That's because we have 4 training examples, and we're taking the average of those 4 as our prediction. And mean squared error is exactly as you understand, like the mean squared error between like the prediction that we're making and the true values of the sale price. Any questions about this first step? Does that make sense? Oh, is there a question? Yeah?
Sorry.
Which one?
What is the
Mean squared error, yeah. So I will write that down. So the mean squared error is sum of y true So essentially, you're summing over all the data, and for each training example, you're taking the difference between the true value, so the true value is like the sale price there, and your predicted value, and you're like squaring this difference and summing over the data set. And since it's an average, you're going to divide by the number of examples in your data set. Cool. Any other questions? Cool. Now, step 2. So the next step is, I guess, the actual training part of the step. So given this data, our model determines the best split. And so here's what I mean by split. You should be able to order some column in some way and like draw a dividing line such that you can make these 2 children nodes in your tree. And the condition is like the average value for each of these children should have like the lowest mean squared error. So what do I mean by this? Like more concretely, in this example, let's say this best split is by overall quality. And so here I sorted by the overall quality, and it turns out like this best split is right here. So the first 3 examples are in one half, and the last example is in another half. And then we split our tree. And so 3 of the examples belong to this node, 1 of the examples belongs here. So the value we're predicting here is the average of the top 3, whereas the value we're predicting here is the average of the other half, which is just one thing. As you can see, the number of samples is 1, as you expect, it's just 1 example. And mean squared error for this branch is 0, which makes total sense, right? Because there's only 1 example here. And so if you follow this decision tree all the way to the bottom, you're always going to predict this. On the training data, you're going to do perfect. Like you're always going to get that 230,000. Whereas in this other half, we're predicting the average value of the top 3. And so this average value will have some mean squared error. Because like all of those don't match the value predicted. That was like probably the hardest step. Does anyone have any questions? Yes. Good question. So basically, Scikit-learn will try every possible split in all your features of your data. And so it'll go through each column and try each of these. Like it'll try like, oh, let's sort by overall quality. Let's try like just the first and the last 3. Let's try 2 and 2. Let's try 3 and 1. It'll do the same thing for year built, like sort by year built. Try every single split, and essentially it decides based on like the lowest mean squared error that you get from the resulting tree. Does that clear it up? I think it'll become more clear as I start to make more. Hopefully. Any other questions? Yep.
So is that based on the condition given that quality is below 0? Is that based on that?
Sorry, is that based on?
It's based on the split. It's based on mean squared error.
Exactly. So based on the resulting mean squared error of like the tree that would happen if we split. So when we split by overall quality is less than or equal to 7, basically we're making this split in the data. And so the resulting model has like some mean squared error if you use it to predict values on like this data set. And so whichever one of these splits like produces the minimum mean squared error.
And in this case, splitting it there gives you 0 because it has to be. In that case, like, it's possible.
Good point. So that's not entirely correct. So I wouldn't look at the individual mean squared errors of the actual nodes. But what you can imagine is now Scikit-learn, or actually, doesn't matter what the library is, the decision tree will now be used to evaluate on all this data, and then you're going to compute this mean squared error on all the data. So really, like these two individual mean squared errors don't mean too much. It's like, all right, cool. So this is let's pretend this is your whole tree. We're going to use this to predict values on like this data set. How well does it do? Cool? Great. Anything else? Awesome. So we're just going to continue doing that for our data set. And so here, since the false branch is like done, we're just going to focus on the right side. And so we're going to continue doing that. Oh, so as you can see, so since like the right branch is done, like we branch all the way to the bottom, there's just one sample. We're not going to focus on that sample anymore. We're just going to focus on the other side of the tree. So now there are just 3 examples that correspond to this node right here. And so once again, we are going to like try every single split in our data and determine the best one. And so this time, turns out the best split was based on this year built feature. And the split was like right here in the data. And so as you can see, the split is if year built is less than 1975. Does that next step make sense? Any questions about that? Don't worry, it's like the hardest part of the workshop, so yes.
So just a question about how you, so again about like how you decide whether it was smart. So if you're gonna check like every combination of features, isn't that like exponential runtime basically?
Yeah, so for the purpose of this workshop, you can say that it does check every single feature. Of course, when you implement it in the library, there are more efficient ways of doing so. But conceptually speaking, you should be thinking about as, yes, it is checking every single possible. So, yeah, good question.
You end up with stuff where you have like only one possible event or
Exactly. That's something we're going to touch on later. Good point. Anything else? Yes.
Right, so this is the first like workshop. So basically, what's happening here is that it's trying every like combination, possible combination of creating like conditions, right? And it's going to get like conditions.
Yes.
And it's going to split it off to see like it's going to compare like creating like I guess like prototypes and it's testing and like to see like how much error it gets.
Yes.
And then when it gets something like when it hits a point where MS equals 0, then you know that's a good branch.
So it won't be MS equals 0. So we'll see in the next example.
Oh, it might not be, but it's good.
Yeah, it's the best one. So it's not like just the MS equals 0. Right? It's like the it's over the entire data set.
Yeah.
So yeah, so the lowest one over the entire data set.
And then that's like the next branch. Right?
Exactly. Yes. Cool. I'm just gonna skip to the end, like pretty quick. So the next best split is among the your build, and then finally it splits all the way down. And so now we built this tree where we split up all our data. All of our leaves only have one data point each. So this is like a fully constructed decision tree. It like it's able to like make decisions and branch down until there's only one example, and so the prediction is whatever value that example is. Any questions about building the decision tree? Yep.
So is it always the same attribute, like all the way down to the top to the bottom of the tree, or could it be something different?
Good question. It could be different one. In this example, it's super tiny, only 2 features in like a small tree. It like the same one. But if you go back to which is worked. if you go back to this example tree right here, as you can see, like there are different features all over the place. Features can be used twice, as you can see, but a lot of the time they're different features. And as you can see, like at the very bottom here, like I've cut this tree off early, and so like this value is like the average of 3 different examples. Like this value that's going to predict is the average of 156 in the data set, and so it can get much bigger. And if you can imagine, like when you actually fit a decision tree to your data, it'll be a huge tree. You will not be able to visualize it like this. Yeah. Good question. Anything else? Cool. So now we did the hard part. Now the easy part. We made Scikit-learn into a chorus. And this is how easy it is to do it in Scikit-learn. So we make our model, which is like a decision tree regressor, which is an object from the Scikit-learn library. We literally call model.fit on our training data. So our training data includes like the X values, which are our features, and the Y values, which are the sale prices. And we're done. And then we can print the score. Yeah, super easy. I told you, the hardest part was doing it by hand. And so a couple things you might notice here. First thing is the training root mean squared error is 0, and the training R squared is 1. The thing I told you before, mean squared error, lower is better. This decision tree performs perfectly on our data, which makes sense, right? Like it like memorizes exactly what our data set has. Sorry?
So it's definitely overfitting.
Exactly, right? Exactly. And so, but if you can look at our validation, our MSE, like this data that we didn't use to train our model, like it's not performing too hot, right? It's the errors, like the root mean squared error is $32,000, which means that you can kind of think of it like on average, the model is like $32,000 off. And as you can see, the valid R squared is actually not bad. Like of 0.9 is like really good. If you look at, so like this is like a really toy example of this toy data that I showed you. In real life, if you got like an R squared of 0.9, like you'd be pretty happy. Like that's super great. But for this example, we're definitely going to do a little bit better. I remember on my co-op term, like a year ago, I like started doing stuff and then I fit my model and I had like an R squared of like 0.13, and I was like, where do I go from here? It was just awful. I had no idea what to do. But no, in real life it's a lot tougher. But this is a nice example. So questions about anything or why these numbers are here? Or anything that I said? Yeah, people that came in late, yeah, please feel free to ask me like questions about words that I say because like I'm happy to repeat them. It takes 2 seconds and it'll definitely help you out. Yeah, and so the main problem here that we identified is the model is memorizing our data. We don't want it to do that. Instead, we wanted to learn some general trend in the data. So we're going to move on to a model called a random forest. Before we do that, there's a couple of concepts that I want to cover. The first thing is an ensemble model. And so an ensemble model is basically a model whose prediction is the average of many models. So for example, you could have many decision trees that you build, and the prediction will be like the average prediction of all of those. The next thing I'm going to talk about is a concept called bagging, or bootstrap aggregation. And so essentially, it's an ensemble model where each model is the same type, but each model that you train sees like a different portion of the data. And so this is done through a concept called bootstrapping. Bootstrapping is essentially sampling with replacement. I said that probably doesn't mean much to you, but I will give you an example. Let's say, for example, our data is just 1, 2, 3, 4, 5. Like, that's the data we have. So, okay, well, normally you'd have like an X and a Y, but just ignore that for now. So normally, you would fit your model on like all of this data. But now what we're going to do is bootstrap aggregation or bagging. And so the idea is we make new training sets for a model to use, sampling with replacement. And so sampling with replacement looks like this. So I would choose like a random 5 samples, but elements can repeat. So for example, it could be like 2, 1, 1, 4, 5. This could be like one data set. Our second one could be like sampling again from this original. I don't know, like 5, 2, 2, 2, like 1. Like that's possible. It's unlikely, but it's possible. And our third one could be like 1, 2, 3, 4, 5. By like pure chance, somehow we got all of them. So that's bootstrapping. So bootstrapping is the process of creating these new training sets from your original by sampling with replacement. Any questions about Bootstrap? Like what I just did here? Great, cool. And so the idea is exactly what I just said. A random forest is a model, which is an ensemble model of decision trees. And we use this idea of bagging. So each decision tree is trained on a different training set. We make these training sets by bootstrap sampling from our original data. So basically, each of these models trains on a slightly different portion of the data. Does that make sense? I can repeat that. Any questions about what I said? Yeah.
Just answer it. It's so
Exactly. So the key concept here is that we will see a little bit later as well, but I'll say it now as well. The idea is that these models are all wrong a little bit, right? Each of these decision trees has some error. None of them are perfect. But the idea is that on average, they're learning the right thing. And so when you have a bunch of wrong models or a bunch of weak models and you average their predictions, in general, they'll do better. And the key caveat to saying this is that the models need to be uncorrelated in some abstract sense. And the idea is that each model should be learning a slightly different thing. Because if you imagine if each of the models are learning the same thing, then on average, they're all going to be the same kind of way, right? You want each of these models to learn something slightly different. So on average, they're producing the right prediction. Does that make sense? Any questions? Yes.
So that's how you know where they're 1, 2, and 3 are the top circle.
Yeah.
Must be different models.
Yeah, I just wrote 1, 2, 3 to represent different training sets that produce different models. Anything else? Cool, great. So how are we going to train a random forest? Just as easy on Scikit-learn. A random forest regressor model.fit. Scikit-learn is a super great library. It's super easy to use. And so already we have a better model, as you can see by these numbers. Training-wise, it's a little bit worse, but we really don't care how well this model does in the training set. We care about how well this model is going to do in action, in real life. And so we're looking at the validation, and clearly the root mean squared error decreased, and our R-squared went up, which are great things. 2 notes. First thing you'll notice, R-squared didn't go up by that much. Root mean squared error didn't go down by that much. In real life, when you're working with your actual data, this will be a very different story. The decision tree will be absolute garbage, and the random forest will do much better. This toy data set is very easy in quotations, and so both models do pretty well. But once you start working with real data, you'll see that these random forests really beat out the decision trees. Flat out. Any questions? Yes.
Validation.
Yeah, good question. So in the beginning, I talked about training, validation, and test sets. So a training set is what you're training your model on. For the purpose of this talk, just think about validation and tests being the same thing. But essentially, they're data we didn't use to train the model that we're using to evaluate the model. In the coming slides, I'll make a distinction between the two. But for now, just think of them as data our model hasn't seen yet that we're evaluating its performance on. Yeah. Anything else? Yeah.
So it will print the best score at the end?
So this is not the best score. This is just the score of the model that we trained.
It's going to make different decisions, right?
It'll take random forest is the average of those decision trees, and so it's evaluating the Y prediction is the average of all the decision trees. Yeah. Anything else? Yes.
So it makes me think of the overfits and the underfits in each of the different decision trees that averaging out to the right score. Right?
Exactly. Yeah, that's exactly what's happening. Yeah. Cool. This workshop will go slightly over time, which is okay because there's no workshop right after it. You guys can leave if you want, but second half is a cool half, I promise. I will explain this. So, hyperparameters. In the beginning of this talk, I talked about how we have to tune these hyperparameters, and I'll explain what these are now. Essentially, hyperparameters for your models are things that you set yourself. And so, for example, in the very first decision tree I showed you, I limited the depth of the decision tree to 4 levels. That's a hyperparameter. Or you can limit the number of examples each leaf node has. That's a hyperparameter. So these are things your model won't learn from your data that you have to set yourself. And for the random forest, I am going to talk about 3 of them. In reality, there are many, many more. You can check documentation to see them. But in my experience, like, these 3 are sufficient to get a pretty good performing model. First one is number of estimators. And really, this is the number of trees in your forest. Yeah, trees in your forest. And so more is always better. The more trees you have, the more powerful your model will become. Of course, it'll plateau, and you won't get some benefit after a certain point, but more is better. So basically, you want as many as you can get without consuming too much time or memory. When you're prototyping, I typically use 30. You may want to use slightly more depending on how large the data set is, but in my experience, like 30 is like pretty good. The second thing is this min samples leaf. So these are just arguments you can pass in Scikit-learn, by the way. And so basically, when we showed a decision tree in the beginning, we showed that it goes all the way down until each leaf has 1 sample. We can actually control this and say maybe we want more samples per leaf. And so if you think about it, it'll average over more examples for the predictions, and so the predictions will like have less variance and it's less prone to overfitting. We'll touch on this in the next slide as well a little bit. Here are some decent values, and increasing the value decreases overfitting. The last thing is max features. I guess this is the hardest one to understand why we have to use. And so the idea is, right now, by default, our model, it looks at every single feature when deciding a split. And so I told you guys it looks at every possible combination of features and like values among those features. This max features hyperparameter basically lets you tune that value. Maybe you only want to look at like a third of the features each time, or maybe you only want to look at half of the features each time. So choose a random half of those features and only look at all the splits in that half. I will explain why we do this in the next slide, but apart from that, are there any questions about what these 3 things mean? Great. So it may seem weird to you, right? Like, why would we consider fewer features for each split? Our model will only get better if we can split on a better feature. And the core idea is this. The power of each decision tree really doesn't matter. What's important is that all of them are relatively uncorrelated, and so the average of the predictions are close to the true value. And so in order to like promote this like uncorrelation, you basically only let each decision tree work with a subset of the features at each split. Because if you think about it, if you look at your data, if there's one feature that's super important, then each model is going to always split on that at the very beginning. And that is going to produce like decision trees that are all very similar. So they're all going to be wrong in similar ways, which is not what you want. So if you only consider a fraction of these features at each split, the models will be more different, and so your predictions of your forest will be better on average. Any questions about that? About why we do this, or how we do this? Yep.
Sorry, I didn't get it. So you're talking about the hyperparameters.
Yes. What hyperparameters are?
Yeah.
So you can think of these as arguments you're passing into Scikit-learn. So here I pass in num estimators. You can also pass in like any of these other 3. And these are things that you set yourself. So your algorithm won't learn it from your data, but you have to set these yourself for the model to work. Anything else? Cool, yeah. Okay, now we're going to go on to the fun part of the workshop. Ooh, there's like 5 minutes left. You guys can leave if you want, but I promise this is interesting. And we are going to look at how we can understand our models. So now we have a pretty good model that we fit on our data after we do some like adjusting of our hyperparameters and etc. But really, we want to continue to improve our model and understand what predictions our model is making. I think that's kind of the most important part of machine learning that a lot of people ignore. Everyone just focused on getting the best possible model. But in my opinion, it's very important to understand what your model is saying about your data. And so that will help you improve your model and also like provide some insight for your company or for yourself or whatever cause you're supporting using your skill set. The first thing we're going to talk about is something called feature importances. So feature importances basically tell you how important each feature is for your model. And so basically, how helpful each feature is for the predictions. And so I'm not going to go over all these questions for the sake of time, but I encourage you to read them and think about these when you look at feature importances. But for now, I'm just going to tell you how to calculate that. And so the specific name for this is called permutation importance, if you want to Google it, but we're just going to call it feature importance. And so we're going to do the following. Basically, we're going to shuffle each column. So we have our data set, which is, we have columns which are our features and different values for each example. Essentially, we're going to shuffle each feature, so it's like uncorrelated now with our target. Then we're going to evaluate the model's performance on the training data set. And essentially, how much worse the model does from like the actual feature versus the shuffled feature is how important that feature is, which intuitively kind of makes sense, right? Like, okay, now consider this feature to be useless. How well is this model going to do? And so it'll tell you how important that feature was. Any questions about how you calculate this? Yes.
Even the target.
Target is like the y value. Yeah. Features are like the x, target is like the y. Cool. Super easy in Scikit-learn. The models have like a feature importance property. You can plot them. You should ask all those questions that I listed on that slide. And you should be playing around with this. So what happens when we remove less important features? Often this will reduce overfitting because for reasons we will actually see in coming slides. And so you should really play around with, okay, what happens when we remove these less important features? Let's look at these more important features. Can we make them more useful to our model? For example, if the date turned out to be really important, maybe we want to somehow extract more information out of this. We can create new features like the day of the week, the season, the month, and so the model has more information to work with in order to make its predictions. And since we saw that day was super important, this could be a really useful thing to do. Okay. Moving on, the next thing is identifying correlated features. And so you can think about correlated features as, so basically looking for correlation between features, and I'll explain what that means. And so when you say a feature is correlated, basically we're talking about how much does one feature vary with another, or how much can one feature be used to predict another feature. Does that make sense? So if like two things are increasing the same way, like they're correlated. For example, let's say you have, for some reason, you have two columns in your data set. One is like the size of your house in like square footage, and the other one's in like square meters, for example. Like these two things are perfectly correlated because they're the exact same thing, right? Except in a different unit of measure. So you want to make sure you can identify these. And so by removing features that are correlated, you do a bunch of great things. The first thing is you reduce the dimension of your data. Typically, when you have fewer features, your model will do a better job of learning them. If you want to read more about this, it's called the curse of dimensionality. You can read about it online. I will not talk about it because of time. And also, when we remove correlated features, our model becomes more interpretable. Because when you have correlated features, this model is essentially taking advantage of one like root cause effect and like two examples of these cause effects and like learning it. It'll increase overfitting and make the model less interpretable. And if that doesn't make sense, don't worry. But essentially, removing correlated features will help your model be more interpretable. Any questions about like those first two things? We will move on. If you don't understand this, again, the ML course that I listed like talks about these in great detail, so it's a great resource to go to. For the sake of time, I am going to, yeah? It's on the slideshow. I'll put the link to the slideshow at the end. I will skip correlation because, how to calculate correlation, just because time, yes?
Sorry, this is sort of an early question, but like, why would we be using like a random forest model this when like something like linear regression also this like what's the advantage of using this method?
Great question. I'm really glad you asked. So, random forests are an extremely robust class of models, and I probably should have explained from the beginning. They are, for a lack of a better term, very idiot-proof. Like it's hard to get that wrong, and this is really great for a couple of reasons. Let me first actually talk about why linear regression may not be the best choice. So linear regression is very hard to deal with in some ways. So for example, if your data is not linear, you're going to have to introduce like non-linearities yourself, which is like complicated. It's not complicated, but it's more work that you have to do in order to get your model to fit your data properly. With this random forest, as you saw, like even though really you should have an idea of how your response looks like a distribution. Like, we had no idea, and we fit this model with like no hyperparameters, and it did fantastic. And that's generally true for random forests. And the rule, like, really what's really great about these is once you get some data, once you do some initial cleaning, you just fit a random forest and see how well it predicts your response, right? And so you might get like a reasonable thing like 0.6 or like 0.5, and like then you know, okay, so there is some potential in this data. If I work with this more, I'm going to result in a good model. But if your R squared is like 0, for example, then you're like, that doesn't make any sense. Like, so you're telling me that this data, this y value can't be predicted by any of our data. That's like a good opportunity for you to go on further and be like, okay, so what's wrong with this data? Or are we doing the right thing? You can talk to people within your business, like experts who actually like were involved in the data collection process and talk about what's wrong. And so that's the reason I present this random forest model to you guys today, because first of all, they're extremely robust. Like no matter what you do, they'll do okay. And if you tune them well, they'll do great. And so this is why I think this is like an excellent choice for many, many tasks, which is why I taught this over linear regression. Right? Cool. Do you guys mind staying for like 15 more minutes? I can cover Spearman's correlation. Cool. Okay. So the next thing I want to say is, when you guys typically think of correlation, you think of like linear correlation. So is there like some line that you can fit through the relationship? So this makes a lot of sense for a model like a linear model, for example, because linear models literally are using the linear relationship. But if you think about how we made our random forest, that's not true of the random forest, right? Our random forest is looking for divides in our data that split the data set into two halves. So it doesn't care about linear relationships, it just cares about the order of our data. Does that make sense? When I say order, I say that because we're splitting the data into two halves based on greater than or less than. Cool. So in order to measure correlation in terms of the order, we're going to use a metric called Spearman's rank order correlation. Long words. You don't really have to know about the specifics. I will teach you how to calculate it, but just know that it measures like the order of the data. And I'll give you some more intuition about this in the coming slides. Equation, ignore it. Cool. So let's calculate rank correlation on some data. So we have the year built and a lot frontage, for example. We're trying to calculate our rank correlation. First thing is we sort by one of these columns and we give it a rank. So the rank is basically what position it is in the data if it was sorted. We'll do the same thing for the lot frontage. So now we sort it by lot frontage, give them a rank. And we literally do linear correlation on these ranks. That was very fast. Any questions about the procedure? I'll give you some more intuition on the next slide. Yeah. In this call, so the columns. Yeah. So let me give you some intuition about what rank correlation means. So I have these plots, and I have Spearman correlation versus Pearson. Spearman's rank, Pearson is linear. And so as you can see, the rank correlation in this one is 1. That's because you can see that there's like a perfect like monotonic relationship. Like you can perfectly, like the position of the x value within the data perfectly predicts like the position of the y value in the data as well, because of the order. The second one shows like a low value for both because there is no real trend. The last one, we can see that the rank correlation is pretty high because it's like, it just looks at the order of the data. It doesn't really care about the actual values, whereas linear correlation will look at the actual values. I'm super sorry, that was super fast. But any like quick questions about what I just showed? Okay, we will just take a look at how to visualize these things. Again, I would check out the notebook later on for some more details about how this works. But essentially, we can use this code here to calculate the rank correlations between all the features and visualize this in a heat map. And so basically what this heat map is showing is, all right, between overall quality and lot area, this is the rank correlation of this color, and you can see the color on the color scale. And so this is super useful for identifying correlations in your data, and you can also like remove or work with correlated features. This is another way to look at the same thing. We are looking at correlations once again, but in this case, basically if they join closer to this axis, then they are more correlated. As they join higher up, they're less correlated. I really love this view because it shows you relationships between values in your data. And this is a super useful way to improve your models, right? So these two things are, like these two things are very correlated. And maybe you want to take a look at your data and say, okay, which one of these features is more important? Then you can try removing the less important feature and seeing how your model does. And a lot of the time, or some of the time, this will improve the performance of your model, or it may not. And either way, you should look into why that happens and continuing to look at how to, continuing to do this process. And it's also super helpful because if you have, you can identify features that rely on other features. Like for example, I'm pretty sure overall quality relies on external quality in some way. That's useful to know. That's probably something you should deal with in your data. I'm going to show you one last thing, and then I'll open the floor to questions. The last thing is tree interpreter. And so the basic idea here is that you want to understand how much each feature contributed to your prediction. And so this is very non-trivial to do for a majority of models, but this is actually really nice for the tree. And so essentially the idea is you want to understand, so you have some average predicted value in your entire data set. You want to understand, okay, which features contributed to my prediction be different from the average. I'll show you exactly what that means in the next slide. Cool. So this is a quick example of computing feature contributions. And so essentially, you can look at this first branch here based on overall quality. And you can see that the average prediction, which is 183,000, it went down to 167,000. So if you think about it, because this example had an overall quality that's less than 7, the prediction actually decreased. And so we can do the same thing for year built. Since the year built is less than 1975, it goes down to this branch, for example. And so you can think of that as, okay, since the year was less than this value, our example had some prediction that's less than this mean. And so we can take, stop moving. So we can take the average of these changes to understand how much each feature contributed. That was quick. Do you guys want me to repeat that slowly, or any questions about what I said? Yeah, so you can look at the notebook for some more information, but essentially think of it as, all right, cool. So given the data that we had, and given the model that we've learned, this model predicted some value of, let's say, 170,000. Because the overall quality was 4, this value of 170,000 is about 15,000 less than the average of the data. Because the year built was 1970, the prediction was about 1,300 greater than the average of all the data. Does that explanation make sense? Cool, great. And so this is super easy. This is not Scikit-learn, it's a different library, but you can look at the code later. It's super simple, and you can get some really nice things. This is super great in a business setting. Imagine you're working at some company, let's say you're imagining, okay, so let's say you're working at a hospital, and you're trying to predict whether someone has heart disease or not. And the doctor asks you, okay, so you predicted that this person is going to get heart disease. Why is that the case? What is your model saying that means this person will have heart disease? And if you use a model like a random forest, you can tell them exactly what your model's thinking. Okay, so this model looked at this data. Oh, given the fact they have high blood pressure, that made them slightly less probable. Since they have an active lifestyle, it's slightly less probable, whatever. And you can tell them these exact details. And so that's a super powerful feature of these tree-based models. You can't do that with every model out there. And so I think this is something you should definitely take advantage of. And the second thing is, now you can take a look at if things are weird, right? I didn't look at that table closely, but let's say, for example, your model is predicting, oh, this person should have heart disease. It's more likely that they should have heart disease because they have an active lifestyle. That makes no sense, right? Their chances of getting heart disease should be lower if they have an active lifestyle. So that indicates something that you should be looking at. Is your model learning the wrong thing? Is there a correlation in your data that's causing these issues? Is there something wrong with the data? Is it corrupted? And so it's super important to look at those things, and this is a great way to peek into your model and understand what's going on. So just a quick recap, we introduced machine learning. We talked about a couple different models, decision trees and random forests. And we talked about how to peer into them, how to understand them, how to look at your data, how to augment your data to make your models better, and really understand what's going on under the hood. So there are a bunch of next steps. So again, I told you this workshop is like a talk, super high level. I'm really just introducing these concepts to you. I highly encourage you to investigate each of these in more detail. The first way to do that is to go to the link Collab, which the slides link will take you there, which I'll show you soon. Go through that code, play with that code. Honestly, the best way to get better at doing machine learning is to actually do it. It's a great thing to practice with different data and really understand what's going on. Take the fast ML course. It won't take that much of your time, but I promise you, you will learn tons. It is fantastic. The next, some other things that we didn't cover in this workshop. So data cleaning and feature engineering. My previous workshop covered this in some detail, but honestly, I encourage you to look at what people do online. There's a link there. I hope it's to someone else's work. Probably is. To show you. Talking about choosing a metric, I kind of just forced you guys to use mean squared error and R squared without really talking about why we should be using those two. I gave you some intuition, but not too much. So that's a good thing to look into. Classification models. Today we talked about regression. On the other hand, we should be talking about classification. So the example I gave about predicting whether someone has heart disease, someone will get heart disease or not, the classification problem. And finally, partial dependence plots. Those are super cool too. They're in the notebook, but I didn't have time to explain them today. Again, feel free to reach out to me if you have any questions. I will be here for the rest of the day as a mentor. I'd be happy to go through these things in more detail with you or help you out with your projects. Yeah, thanks for listening. Here are the links.